Alright, here goes the quickest Calc 3 video in all of mathematics. The divergence theorem, last section in chapter 17. Divergence theorem is the three-dimensional version of the flux form of Green's theorem. So we did the other version before with Stokes' theorem. This is the flux form. This is the divergence theorem. So instead of integrating the flow across this boundary, you're adding up all the sources and sinks throughout the region, and it uses a triple integral over some region D. Now I said the theorem's two parts are integrated over different regions. The double integral is done over a surface. The triple integral is done over a volume. So when I show you the formula, you'll see that you're actually integrating over two different things. All right, here it is, the divergence theorem. You notice in the first one, you're integrating the dot product of the vector field and the normal vector over some surface. In the other side of the divergence theorem, you're integrating the dot product of the del operator and the vector field over some volume. So the left side is going to require that you know those outward normal vectors. The right side does not. So you're going to need the del operator and a dot product. I know this is different because in the past we've done cross products with the del operator. This one is going to be a dot product of the del operator and the vector field. Easiest way to do this, let's take a look at an example or two. So I want to find the net outward flux of this surface, and my vector field is x2, y, z. The surface is the boundary of a tetrahedron in the first octant that's formed by that plane. You know, a tetrahedron is made up of four triangles. If it's a regular tetrahedron, then it's just four equilateral triangles and you're done. But the tetrahedron is made up of four triangles, all the same. All right, so if it's bounded by that plane, x plus y plus z equals 1, the first thing we can do is we can find the dot product of the del operator and the vector field. So that means take d dx of x, then you're going to take the partial derivative of 2y, then you're going to take the partial derivative of z. So this will give you 1. Partial derivative of 2y with respect to y will give you 2. Partial derivative of z with respect to z will give you 1. 1 plus 2 plus 1 is 4. So what I'm doing now is I'm looking for the triple integral of 4 dv. Now I could try to set up all different types of equations to figure out what that is, but wouldn't it be nice if I could find the volume of my tetrahedron? Well, if it's formed by this plane, x plus y plus z equals 1, what if I let z equal 0? All right, so a little bit of scratch work on the side. If x plus y plus z is equal to 1, look what happens when z equals 0 when you're on the xy plane. You get x plus y equals 1, which means that you're looking at this thing here as the base. Well, I've got now a triangle, right triangle. Base is 1, height is 1. The area of that triangle, or the base of my figure, is going to be 1/2 times 1 times 1, which is a half. All right. Now, how do you find the volume of a pyramid? Because that's what a tetrahedron is, right? It's got a triangular base and triangular faces, so it's a pyramid. Volume of a pyramid, go back to geometry formulas. 1/3 area of the base times height. Well, the area of the base we just calculated is this triangle here, whose area is 1/2, and the height of the tetrahedron is just 1, right? Because if it's in that plane and x and y are both 0, then z is 1. So what is the volume? The volume is a 1/6. And that can save me some time because now I can slide over here and I can replace that dv with a 1/6, and I end up with 4 times 1/6. 4/6 is 2/3. So that's the net outward flux, right? More going out than coming in. All right, one more. Let's take a look at a more general region. So here I want to find the net outward flux of this crazy vector field, z minus x, x minus y, 2y minus z, over some general region, the region between spheres of radius 2 and radius 4, centered at the origin. So this sounds horrific, but it's not too bad. It's between two spheres, right? So you've got a smaller sphere on the inside, right? And then a bigger sphere on the outside, and you want to look at the region between those two spheres. Well, first thing is I should take the del operator dot the vector field. So take the derivative of the first with respect to x, and I get -1. Take the derivative of the inside piece with respect to y, and again I get a -1. Now take the derivative of this third piece with respect to z, and again I get a -1. So the dot product is -3, which means I'm integrating a triple integral of -3 dv. Now I got to figure out what the volume is. How do you find volume of a sphere? Volume of a sphere is 4/3 pi r cubed, right? So let's find the volume of the outside minus the volume of the inside, and that'll give us the volume that's between. So the volume for the outside is going to be 4/3 pi times 4 cubed, right? That's the big radius. Now get rid of the little one. So this is the three-dimensional version of a donut, right? Donut, you take the middle out. That's how they make the munchkins. In this case, you're taking the middle, the sphere on the inside out, and you're leaving the region on the outside there. So this will give us 4/3 pi times 4 to the third is 64, 2 to the third is 8. That gives me 4 times 56 over 3, which is 224 over 3 times pi. All right, this now goes in for the dv, and look how convenient that is. We end up with -3 times 224 pi over 3, which just gives me -224 pi. So the net outward flux is negative. That means that it pulls in. Right? If the outward flux is negative, then it pulls in. I told you this would be short. That's the end of 17.8.